You know, if there's one thing I miss about like CRT monitors, it's the fact that I could run them at 75 hertz. Which is a thing that I used to do. 60 was too slow of a refresh rate. We had 75 hertz monitors in the early 2000s. And we gave this up for liquid crystal. And liquid crystal technology hasn't really caught up until like maybe the last, I don't know, 10 years maybe. Liquid crystal. Yeah, the LCD and in the LC in LCD means liquid crystal. And it's not even proper to say that everything is LED because it's not all LED. Are you familiar with the term IPS? These are like high-end displays, as they are often quoted. But like, IPS is a form of liquid crystal technology. It describes like the way the crystals are driven. Plasma still sort of exists, but like it's far less popular because the plasma cells have a very strong tendency to burn in. Where's Kryta? We need Kryta. And your typical display has different layers. It would help if I had like a color that I could draw. So you have like you have like an outer layer, which is the surface. It can be either glass or plastic. And then you have a vector layer, which is not where we want to put that. The pizza. Pizza. I had some pizza earlier. And then you have this crazy sandwich of stuff. This crazy multi-layer sandwich of stuff. So in the front of the display, you have what is called a polarizer. Why is this on another vector layer? Oh my god. sandwich of stuff. And then you have an electrode slash driver. We gotta draw little lines. We gotta draw little lines on things. Very important. And then the bit in the middle. This is the meat. This is the liquid crystal. The liquid crystal matrix. Which is in the middle. And then there's another electrode. There's then the back side here you have another polarizer. I don't think that's how you spell polarizer, but like, who's keeping track of that? I'm certainly not. And then behind that, you got this like, this fuzzy layer. I can't draw without turning the mouse sensitivity all the way down. What is wrong with this mouse? E. Fuzzy layer. Technical term. Whoosh. This thing is called a diffuser. That's kind of very important. And then behind that you have a light source. The light source is either going to be like a CCFL or an LED. So in the matrix of liquid crystal, you have like all these like weird jumbly particle-y things. Technical term. They're like all jumbled and messy and all over the place and whatnot. And what happens is you have a polarizer, which is like, it's designed in like the horizontal direction. Polarizers come in different flavors. And then you have the opposite kind of polarizer on the other side of the screen. So let's say you are a ray of light. That harsh, ridiculously bright, obnoxious blue light, and you come out of the light source. You hit the diffuser, you bounce all over the place. Come out as like a big jumble of light. Whoosh. Going out every single which way. And then you hit the polarizer. The polarizer will reject all of the light. Whoosh. So that only like the straight light goes through. the light that's like in the same direction. And the rest of the light will just sort of keep bouncing around until it gets absorbed as heat or gets through the polarizer. And then it will go into the matrix of liquid crystal. The liquid crystal does something kind of ridiculous. If the liquid crystal is on or off, it will change how the light is polarized. So if it's off or something, the light will just go like straight through it. Or no, I think if it's off, depends on the matrix topology, but like it will flip your light to being like horizontal, and it will go through the filter in the front, the polarizer, and then out of the screen, and then out into the universe. But if you apply, like, I don't know, electricity to the electrodes, zap, electricity will, like, grab the liquid crystal, and then your liquid crystals will, like, they'll sort of, like, line up and twist and whatnot. So if you have, like, some of that light coming in here, and it hits this part of the display, then, like, it'll come out of the LED, it'll get diffused in the diffuser, come out every which way, it'll get filtered by the diffuser, and then if it hits the active part of the display, instead of getting twisted around and flipped, it'll come through with its original orientation. And then, because it's the wrong shape, it will hit the back of the polarizer on the front of the display, and it will get stuck here. It won't be able to get out. This part of the display, where it's off, this shows up as like a very bright pixel. On this part of the display, where it's on or something, is darkness. But depending on like your display technology, some of your light might come in from like this angle, sort of graze through the liquid crystal, and then come in at a slight angle through the front of the polarizer, which is probably easier to draw up here. So it will like whoosh around, and then like a little bit of light will get through. Which is why, like, if you are looking at the screen from like this direction, then like you can sometimes get like little bits of light that leak out at weird angles. Usually it's up or down. And the this is why, like, if you have certain kinds of LED backlit LCD displays, if you look at them at a particular angle, they appear like slightly brighter and maybe slightly washed out, even if they're showing the color black. As for how I learned about screen display technology, I probably read about it in a book some stupid huge number of years ago. I also had like an LCD screen that I had, and I took it apart once. So depending on like how this stack is like tightly packed in here, like the polarizers, these are usually made out of like, I believe these are typically like, they're either made of glass or they're printed on glass. But the electrode matrix here, those are definitely printed on like glass sheets usually. And the electrodes, this is kind of the fun part. The electrodes are like a transparent material that's conductive to electricity. And they make these out of what is called, I think it's like indium tin oxide. Which means that in order to make like display panels, you need a supply of this special indium, which is probably not a material that you've heard of before unless you've dealt with like display technology. Because you need it to make these transparent electrodes. Another thing that you probably would not think of is the fact that like um, depending on the display technology, they might actually etch transistors onto the display surface to drive the electrodes directly instead of like having the display drivers off the edge. Also, I say this is CCFL or LED. CCFL is the old technology. It stands for like cold cathode fluorescent lamp or something like this. And they didn't actually put them behind the display. Instead, they put them off on the edge of the display, and then they replace this with like a giant mirror, and then they like have the lamps shoot at an angle into the diffusers. Which is why cold cathode fluorescent, yeah, something like that. Which is why the old LCD panels were like so thick. Is because they have these like lamps on the sides that and they have this giant reflector on the back. Like if you take the light source off of the back of an LCD panel, like just the diffuser stack, the polarizers, and the electrodes, like all of this stuff is actually like super super thin. Which is part of like how we end up with like such thin devices nowadays. Because like LEDs as a backlight source are also pretty thin. They're pretty small. You can just like cram a ton of them onto a screen. So this is typically the technology that's used for like desktop displays. Because it's like, although it is kind of going away a bit, but they've been making like large scale computer displays, televisions, using like liquid crystal technology for like a couple of years. And by a couple, I mean like over 20 years at this point. But cell phones, on the other hand, mobile devices, they don't do this. Mobile devices, they're little tiny display screens. They use a different technology. Given their density requirements of like little tiny displays and like also like I don't know what I'm trying to say. I don't know, the whole portability thing, energy constraints and whatnot. This is a lot of components. So what they do for mobile displays devices is that they welcome the big book of bug raid. No wait, that's not a display technology. Hello there. Very bug. Very bug. Hello and welcome. How is the bug today? How is the bug stream? Talking about displays. Who did the common Lisp? Did you make anything in particular with the common Lisp? Or were you just like learning the language itself? Wayland bindings. I'm gonna assume probably client side, but that sounds pretty exciting if you ask me. I think some point like a month ago, or within the last month, I made like some Wayland bindings from scratch, but I was writing them in like C++, which is kind of like, I don't know, not the hardest thing to do, but also it was interesting because like I did code generation and stuff for it. What do we have? We need to shout out the big book of bug. This is very important. There I go, putting the word the in front of names again. The bug of bug. The Meisaka. The client is mostly completed. The bug of 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 bug. Well, if you need a little break after streaming, don't let me keep you from getting some of that delicious liquid refreshment or something. I have tea today. It's pretty good, but it's also warm when I pour some out. I made myself some chai. Dinner. Dinner. It is the L:Q. Also bugging. Also bug. Wait, there's Kirim from the raid? Double dipping the streams, I see. Let's talk about displays here. Before the raid came in, I was explaining the inner workings of the liquid crystal matrix. And was about to mention the mysteriousness behind mobile device screens. Mobile devices use a different technology, which is called OLED. But like the LCD screen, they have electrode plates on both sides. But instead of having liquid crystal in the middle, they have a special compound which is called like organic light emitting diode. And they put this in the middle. And it's called organic because it's like made out of like it's made out of like organic compounds, as they call them. So like it's like got carbon and hydrogens and oxygens and maybe nitrogens. I don't know exactly, but it's like it's another way of saying it's non-metallic. But when you send electricity through this material, it will emit a wavelength of light. So there's different compounds for each individual color. And the way the display matrix has to be built is that like you take like one of each color, and you usually pick like the 3 primary colors. Of course, having like the front of the display exposed like that is usually not very good. So in the back they put like they'll put like they'll either put like a mirror or like an absorbent layer. Because they don't want incoming light. If light comes into the device, they don't want it to like bounce off and then make the display completely blinding. So usually it's going to be like light absorbent material. And then in front of that, there's usually a protective sheet of glass. And then on the surface of the glass, they put more electrodes and stuff. Because most of these devices are like they're usually like touchscreen devices. So they put like a touch digitizer. In the front of the display. So you got your glass, you got your touch digitizer, which is like this whole stack. And then in the front of that, there's like another layer of glass. And this time, that's like the outer layer of the display. So that part of the glass is usually like some sort of like it's usually some sort of flexible like infused glass that's like scratch resistant and somewhat shatter resistant. I'm not going to say perfectly because if you drop your phone from like 2 meters up, it's going to break. But like it might also not if you have like the appropriate case or something. And this whole entire stack, you think like, oh, that's a lot of things. But all of this is less than 1 millimeter in thickness. Less than or equal to 1 millimeter. Which is kind of, sort of, vaguely impressive. The other thing of note here, when it comes to like OLED displays, is actually like the fact that they I'm gonna grab like a palette here. Can you let me use this? If I want the pure red, if you were to look at the front of like a modern like mobile phone display, most of them have a pattern that looks sort of like this, where it's like red, and then they have like this little thin strip of green, and then they have like a blob of blue, and then they have like another strip of green, and then they have like red again. I don't know if I can draw these perfectly to scale. And then we have the green again. And they'll have like another blob of blue. And then it will just like keep going like this across the display. And you might think like, well, wait a second. If you've heard anything about like displays, isn't it like RGB? There's twice as many greens as there are reds and blues. And you might be right about that. mobile phones have like these weird this weird mixture of stuff here. Gotta sandwich the LEDs. And also, I kind of deliberately drew the blue one bigger than the red one, and there's a very good reason for this. You see, when it comes to like the organic display materials, the ad breaks tend to show up in the middle of like what I'm doing, and then I'm like, well, shoot, I gotta wait for that to go away before I do anything. Otherwise, you wouldn't be able to hear my explanation about like why the colors are the way they are. That wouldn't be good now, would it? I certainly don't think so. The more green receptors, I mean, this is sort of a little bit of a part of it. But the reason is actually a little bit crazier than that. Well, maybe not all that crazy, but like, there's a very, very specific reason for it. I want the ad break to go away. Gotta see those bushes. We don't know about the bushes. The leafy bushes. Anyways, now that that's gone, I can probably resume my explanation. Maybe. Maybe. So, if you were to look at this thing, there is sort of like a logical pattern here that you could like sort of conceptually like say that like, oh, this is a pixel. If I forget to not fill my squares, that would be great. Yeah, nope, gonna be on the background. So you could almost think of like, this is a pixel, this is a pixel, and that was sort of work. But why did I draw them like this? Well, I sort of mentioned earlier that the materials are organic compounds. The organic compounds being made out of like some slurry of chemicals that have stuff in them. Well, if you pass electricity through the organic compounds and then they start glowing brightly, some of them start to deteriorate. Some of them will glow brighter than others. What's for dinner? Organic compounds. My favorite. So, the materials for light emitting organic light emitting diodes are such that the red actually emits the most light. For a given input unit of energy, the red material will emit the most light for the same amount of power as the other elements. Which is great if you need something to be red, and not so great if you need something to be any other color. Green is weird. Green also kind of emits quite a bit of light. But green has a quirk. Humans perceive green more strongly than the other colors. So you might say that, like, we're an equivalent light output amount. Red and green are like equivalent or something. But they're not. Green kind of emits the most visible, perceivable light, partially because it triggers not just like the green like color receptor cells. It will actually also trigger like the generic light receptor cells, which are the rod cells as they call them, which are your generic bright and darkness receptors. And so if you need to like if you need like some high resolution perception, you have a lot more of the rod cells, the like light and dark receptors. So on the display panel, they double the amount of green, knowing that you'll be able to perceive like the light levels emitted by the green with a lot more precision. So the video processor on the display doesn't actually break up pixels into these little clusters of 4. They actually break up the pixels such that every green is a pixel. And then when it comes to like the red and blue, it will like average the red and blue between the 2 pixels onto like the adjacent red or blue. So like this one here will have all of the red from this pixel. This one here will have all of the red from its own pixel. And then like the red component from this pixel will get like averaged and split in half and then sent to like the adjacent pixels. Same thing for like the blue channel, but like staggered the other way. That way, if you have like something which is sort of fundamentally high resolution, it will use like the green to like delineate pixels because you're more sensitive to that. And then the red and blue, it will just kind of smear those across all the pixels. Blue, I saved this one for last because it's weird. So unlike the red and the green compounds, the blue compounds emit probably the least amount of light. So on the phone display screen, they actually have to like push more energy into the blue pixels, give them more oomph. But this has the downside of making it so that the blue component breaks down faster and it will wear out sooner. Which is kind of unacceptable. Because normally you want your display to actually display things, so instead of making it wear out quite as fast, they just underdrive the red component and the green component to like roughly the same dimness to match what the blue channel actually does, so that the blue channel will last longer. It's all because that stinking blue color. They also have to like compensate for the fact that it doesn't emit as much light by making the subpixel elements slightly bigger. Not like significantly bigger, but like big enough that it produces like a notable amount. So that's sort of kind of fun. However, 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 there's more technologies than just this. Like, if organic light emitting diodes have like all these little problems with like burn-in and like light intensity limits, surely there are no downsides. Well, surely. If I had someone named Surely, they'd be thinking like, hi there. Organic LED compounds have a little bit of a problem. They're difficult to manufacture in like large scale displays. Like if you have to make a display screen, most people are gonna like stare at you funny if your display has like dead pixels. Nobody likes dead pixels. Nobody. So if you make a panel with like, I don't know, 4 million pixels in it, and one of them happens to be bad, then like, you won't be able to sell that panel. Or if you do, it will get used for something like very insignificant. Like maybe like digital signage or something stupid like that. But the defect rate for OLEDs is not very it's not very favorable. So, some number of years ago, there was quite a lot of research into like alternate solar technologies. And if you're looking at me like, but we're talking about displays. One of the solar research projects was like, um, is research into how to make like what are called quantum nanorods, which are like these little inorganic compounds that are like they're long and they got like some receptors or something on the ends of them. Display research stopping after 2008? I can assure you, display research has not stopped after 2008. It just slowed down a lot. But basically, at that point, they were like, IPS LED is great for large screens. Organic LED is great for small screens. Let's just get really good at selling these. Nothing can compete on price. Nothing, I tell you. Well, so there's some research being done, and they make these like nano compounds, which are like little rods that look kind of like something like this. They are of some length, some length. They're like I don't know, some number of like nanometers in length. And these things are being like made in like liquid compounds and they're being used for solar efficiency research. So like you got the rod thingy, you get your zigzaggy wavelength of light. It hits the nanorod and then it produces the zappy zappy. Electricity comes out. Zzz, zzz, zzz. Someone was like, okay, but what if you put power into the thing? Zzz, light comes out. And then someone is like, oh. Except it's not green light. It's like some icky orange color of light that's not very useful. However, the little quantum particles, they can be made of different lengths by like altering the like synthesis process slightly. So like somebody tweaked it to make red light come out. And then they experimented a different way and they got green light to come out. And they filled with it some more and they got blue light to come out. And then somebody is like, we have particles, they're reproducible, they're suspended in liquids, they make all the colors of lights come out of them when you apply the zappy zappy. Oh my god, we could turn this into a display. The papers cited these things as being called like quantum dots or quantum nanorods. So like when they started putting these things into displays, they came up with like I don't know, some weird acronym like whatever it was. What was it called? I think they called it like I think they when they actually started introducing these as displays, they're called like QDEL. Which is like short for quantum dot elect electro luminescent. Which, if that's not a mouthful, I don't know what is. It's kind of crazy. And if you want something more crazy to know about, the people doing this research are basically they're doing that research at the University of Urbana in Illinois, which is 10 minutes away from where I live. And they were doing this back in like I forget when it was. I think it was like 2016 or something. And I remember this because I had to write a school assignment about like cutting edge research or some such. And I was like, oh, the University of Illinois, which is a place that I'm familiar with because like I kind of live around that area, or used to at that time, is doing research on like quantum photonic devices. And I'm like, well, that's fun. So I wrote about that. And I saw these things pop up as displays probably within the last 3 or 4 years, I think. I think there's also like some other term for them. But the way they make these into displays is kind of like it's kind of like the OLED panel in a way, but not quite. So they got their electrode layers. You got your backing sheet of glass. Or no, it's not glass. The stuff on the back of the display, this is called like this is like that ultra black stuff. I don't know if you've ever seen like that super black paint that they have that like it just blocks out all the lights. But basically they take that stuff and they make the back of the display out of it. In the middle here, they have the electrodes. Which are like, you know, your typical run-of-the-mill display matrix thing. There's like an X and a Y, and then they like overlap, and there's usually like some driver transistor in the middle of them. I mean, it kind of serves the same purpose. It's a light absorbent material, but it absorbs like a ton of light. Like a ton of light, way more than the other display. Like the display is like straight up a black hole if it's off. And then what they do is like they put the quantum dots. These things, each one of these has got like a material, and these things are ridiculously tiny. Absolutely absurdly tiny. And then they put the glass screen. So like if this is a phone screen, and these are the pixels on a phone screen, if you were to compare like a quantum dot electroluminescent screen to this, and let's say these are like the pixel area, because of the way the technology works, the quantum dot is like minuscule, and they put them in the middle. If I could draw something that's small, that's actually challenging unless I zoom in. E. My selector thingy. There it is. Where'd you go? So there'd be like one there, one there. So like you have a regular display, and then you have like the quantum dots display, and these things are so ridiculously small. Most of the pixel is darkness. Because if you pass energy through these things, they are absurdly bright. You know, in theory, you could make stuff that exceeds 8K. Even with conventional like OLED or like LCD technologies. The reason they don't is because like the display driver technologies, they don't support like higher resolutions. Like at that point it becomes a bandwidth problem of getting the pixel data to the display panel as opposed to like actually making a display panel of the appropriate resolution. Which is actually why, like, if you want something that's higher resolution, That's why they make bezel-less and multi-panel displays. Because at that point, the bandwidth of the connections being the limiting factor means you have to add more connections. This is also where, like, some of the frame rate limits come from. Have you ever wondered why things tend to top out at, like, what's it called? 240 hertz or whatever? Like, some stuff does go higher, but then you're limited on, like, resolution settings. It's because of the bandwidth of the display standards. You want fragment shaders? Did you what now? Did you what? That's also on top of the fact that, like, you probably can't even get enough, like, compute latency to actually make any of this actually happen or work together or whatever. Proposed 16K? I mean, it wouldn't surprise me. Like, also the terms like 8K, 4K, 2K, all these terms are kind of sort of nebulous. Like, in theory, they're supposed to sort of represent, like, I guess, like, sort of lines of input, but not quite. It's very weird. Like, full HD is what they call. Um, why is this blue? It's typically at, where's my number lock? 100 or 1920 by 1080. And I don't know the, like, 4K number off the top of my head, but I might just, like, look this up here real quick. Yeah, this is it's not actually 4000. It's 3840 by 2160. It's double the numbers of, like, full HD. Why are we tile window? What? I think I broke it. It's weird. This might be called 1K or full HD. And then this one is 4K. And I mean, if you think about it, it makes sense why they might call it 4K. There's 2 prevailing theories. One is that, like, it's like, it is technically 4 times the like pixel bandwidth as like full HD. Another prevailing theory is that like they took the horizontal and just like rounded it up. Personally, I'm of the opinion that it's probably more like, it's probably related to like pixel density bandwidth. Although personally, I don't know. I'd probably find out from Wikipedia. They probably tell me. Maybe. Apparently it's part of digital cinema specification or something. Who knew? Who knew? I certainly didn't. And in that case, it is actually 4,000 something. Can we like shout out the L:"Q? This feels like a must. Darkness. Yeah, what does the Wikipedia tell me? Term 4K is generic and refers to any resolution with a horizontal pixel count of approximately 4,000. And then there's a bunch of stuff about weird standards, which I'm not going to read. But if you want to find out about 4K resolution, I guess that's the place to go. Maybe. Probably. So I was roughly right. It is the horizontal pixel resolution being like almost 4,000, which is why they call it that. You know, this is another thing. Like the vertical pixel count, it's not actually what is called pixel count. It's what's called line count. But this is an interesting conundrum, nevertheless. Like they have 1K, they have 4K. However, there's another term. It's the designation 1080p. Maybe you've seen it written as like 1080p 60 or 1080p 50 if you're in the Europe. These are different from computer screen resolutions, believe it or not. These are actually special resolution modes that are designed for televisions. So, like, if you're not aware, there's actually more of them. And it's not just 1080p. There's also what's called 1080i 60. There's also like 1080i 50. There's also like 720p 60, 720i 60. These sorts of things. These are what are called like television modes. So the P in these means progressive scan, and the I means interleave scan. Which are, again, historical terms for how television works. So in the olden days of like CRTs, there was only so much broadcast bandwidth. But they wanted the picture to still sort of be kind of smooth. But they also didn't want to compromise too much on like display resolution. So they took their screen and like and it's broken down into lines, which I cannot draw multiple lines very cleanly. My artistic skills are like sort of okay with a mouse, but an attempt will be made. There's a bunch of these. So on and so on and so forth down the display. So on a television, there's like a beam of electrons. This is how they used to do television. So the beam will go like, and it will scan across here, and then it will like go off the edge, and then it will go whoosh, and then it will go over here. Which I should probably use the line tool for. Be like across the screen, and then all the way over here, and then down the screen, and then and then zigzaggy back and forth. And if you're like, if you're looking closely at this, and you're like, I didn't draw in the line. I'm like, yeah, I didn't draw in the line. I actually did this deliberately. Because we add a little bit more information here. Be like, this is the part of the screen where the pixels are drawn. And then the beam turns off. And it just keeps going, and then it goes zoop, and then it turns around, and then they turn it on again, and then they scan more pixels, and then they turn it off again, and then they go zoop. Pixels, air quotes. Truly, truly. Also, hello there, and welcome to the trap exit. But if you consider like this part of the screen to be like a line, and if the beam is off for this line, then where did the pixels come from? Well, this keeps going. It scans across the lines, yada 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 yada. When it gets to the bottom, it turns off. And then it kind of goes zoop all the way up here, and then it has to like turn around. and then they turn it on again, and then they go across this line of the display. And then they turn it off, and then it turns around, and then it goes zoop, and then it turns around again, and then it turns on, and it scans this line of the display. So the first time around, it scans all the odd lines. The second time around, it scans all the even lines. And it alternates between the even and the odd lines every other like frame. But they didn't call these frames, they called these fields. So like it actually only hits all of the fields in such a way that it will actually hit both the even and the odd fields every 30 frames. Like 30 times per second. Except it's not actually 30 frames per second. Because that would be too easy. Nope. Instead, it's 29.97 frames per second. Yep, that's a lovely number. Definitely. Definitely nothing wrong there. And this is what is called interleave scan. However, when they quote the specifications on it, they don't count frames per second. They count like fields per second, divisible by some common clock frequency. It is divisible by some frequency, and it's obnoxious. This is probably the most obnoxious frequency. Let's see, what is it? I think it's, yeah, I had to look this up because it's a weird number. So they use a sort of conventional pixel clock, which is 3.575611 megahertz. Which is a little bit of a weird number. And yes. And yes, in fact, it was created because black and white television needed to be like modulated using FM frequencies. And in order to prevent the color or like the, I think it was like the horizontal refresh from leaking into the audio frequency portion of the, the modulation spectrum, they just mushed the frame clock ever so slightly so that it would dephase with the audio subcarrier, and then like and then it wouldn't cause interference. There is a whole entire thing about all of this that you could probably read about. But there's also sort of like an interesting consequence that comes out of this. A lot of the old retro computers used to use a system crystal clock, which is like some multiple of this silly number. And they used to take this number and they used to like chop it in half. So what is that? 1.7878055 megahertz. And then like you could take this weird number and you could like feed it to like, oh, I don't know, a CPU. Because that's something that you might want to do. Yeah, you just take that. You can put that in there. Yummy. And then your CPU can like generate video at this weird frequency, and it will all be very nice. Which is why like a lot of the retro, and I do mean very retro computers and game consoles all had like they all were like quoted as having like one megahertz clock speeds, or like 3 megahertz clock speeds, but not quite. Part of the reason for that is because they would pick one of these like one of these weird crystals for their display driver to make it output for televisions. But like there's a limit. So like this is all fine and good for CPUs of like the 80s, output to televisions in North America. However, there is like you know, a whole other like region where instead of having the screens be like 30 frames per second, they decided they wanted more resolution. Maybe if they tweak the standards for modulating stuff, then like they could get more resolution. Maybe if they refined the color standards, they could also get better color. Enter PAL. Enter PAL. They call phase alternating lines. This was a standard that was like introduced in Europe some number of years later for like a higher resolution. What's it called? Higher resolution color television. And this is sort of partially true. Like they made the screens like roughly 60 hertz that you could potentially synchronize cameras and like video equipment to like using like the television, or not the television, you could use the electric power, the power lines to synchronize the shutters. Although I don't know how entirely true that is, because a lot of it is based on modulation requirements. So like it is sort of it might be sort of inspired, but also slightly coincidental. But I can't imagine that it wouldn't be incidental. They probably had some hand in tying it to like the electrical system frequencies, despite the fact that you need like precision oscillators for this sort of thing. And you can't even use the electrical phase to synchronize any of this equipment because that wouldn't work. But the phase and frequency for PAL is ever so slightly shorter. It's like 20, 25 something. $25 something frames per second. Or roughly 50 fields per second. Why did I say shields? Where did I get the letter S from? Oh, that's where. No Shadow Raid Legends. We don't do that here. We don't shadow the Raid Legends. Honestly, I don't think I would probably ever shill mobile games. Or like overtly mobile games. To be perfectly honest, I don't like mobile games. I don't know that I play any, and if I think the only games that I played that could be arguably considered mobile games also had desktop versions, and I played them on desktop. And the desktop versions were not as good because they were designed for like that weird mobile touch interface thing, and I hate that. If you're gonna make a touch compatible interface, don't put that on desktop because that's not gonna work very well. That's gonna be very unergonomic for people who have mice and keyboards and high resolution screens that they're sitting like 3 inches from or 7 centimeters. Also, by the way, do not sit 7 centimeters away from your display. Your eyes will not be able to focus on anything. This is what we like to call sarcasm. Extreme levels of sarcasm. How long have I been listening to this song? Probably too long. Time for something else. Very. You know, I don't know if I have any other random things to talk about in here. Other than the fact that, like, I went on this whole tangent and I never really kind of explained what this has to do with, like, the television formats or how they are different. Other than what progressive and interleave scan are. Maybe. But I don't even think I covered that. Progressive scan is the opposite of interleave scan. To be like, instead of like skipping every odd or even line, you do all of the lines in one go. Which means that your frames are actually the number instead of being like half of a frame. So like 1080 interleave 60 is, I think, actually technically like 120 fields per second. Maybe? Or is it like, or I don't know if they count that as frames per second. I'm a little bit curious about that actually myself. But if a monitor advertises one of these weird I or like P version display frequencies, these are actually very, very fundamentally different from like these other like width height type ones. Because if you pick one of these type of resolutions, it will the display driver will actually use like what is called the like television video profile or whatever. And the timings for like 1080p 60 are actually different than if you picked like something that's like 1920 by like 1080 at 60 hertz, for example. Like, even though they sort of represent the same like visual representation of resolution, the timings are different. The timings are different, and your monitor will in fact act different if you pick one of these over the other, despite the fact that they have the same like pixel resolution and the same like apparent refresh rate. Subpixels. Tiny subpixels. This is a somewhat vaguely related tangent. But yeah, if you know your subpixel geometry, you can make super duper tiny fonts. However, this only works if you have, again, an RGB video mode. That's another thing. You need to have an RGB video mode. You have to have one of these computer video modes. You can't use one of these television ones, because a lot of these use what is called like chroma subsampling, which is like where your pixels, the color data sent to the display, isn't sent as RGB. It's sent as lumachroma. And then they take the chroma values and they send like half as many or a quarter as many. And the resolution of colors isn't clear enough. And then your text looks all weird and blurry and kind of not all correct. Very, very, very unusual, they might even say. And like, I can sort of demonstrate this phenomenon like on the stream, actually. So like, when you stream stuff, for example, the stream sends and captures video using like this chroma subsampling method. And then it encodes all the pixels in some sort of chroma subsampled way. So if I were to like draw a bunch of like individual pixels, like so, be like, okay, yeah, it's red, and then we stick some blue in here, because these chroma subsample together in very interesting ways. And then we just like copy and paste this a few times. Make it nice and good and pixely. Gotta make sure this is big enough. Oops. This kind of sort of hurts my eyes to look at. But like, if I zoom out to like 100%, like if you were to look at this on the stream, let's see, I think, what was it? Was it red and blue or was it red and green? It might have been green. It's hard to, I don't remember exactly. Let's try some green. Green. Green will probably do it. A lean, mean green machine. Oops. See, I had a way of doing screenshots. Is that you? No. Nope, maybe not. I don't exactly remember how to do it. I'm like, how do I take a screenshot on the Linux? I don't think I have that set up for like, for like the sway, because I haven't done that for a while. Did I have hyper? I think there was a command that I set up to screenshot on Hyperland. And maybe I can use that on here. What are you? Grim Slurp copy. Can we just like screen this, run that? No, not quite. I need to put a sleep in front of this. Let me go back over here. Any second now would be nice. God damn it. It went away. Why did you not go? What do I need to do? Be quick about this? Float the window? I'll just float the window. Because I want this little thing to be on the screen. sort of. Let me put the thing on the screen. Hey. I get the feeling that this is like not what I captured at all. Yeah, this is like not very... It doesn't want to actually capture thing. I'm gonna have to like open up the thing on my other computer, screenshot it, save it to a file, stick it on the network drive. Because this stupid thing doesn't want to screenshot something. And it doesn't want to paste. There we go. There we go. That was way too difficult. Partially because I'm trying to hit like a moving target. You notice how, like, if I zoom into this though, you can sort of see the checkery pattern. But like, this is sort of a yellowish green, and like, this is just straight up purple. Compared to red and green and red and blue, which if you zoom out look like yellow and purple, but they're distinct colors, and over here they're definitely not very distinct colors. This is what is called like chroma subsampling, where like to encode the video, it takes every like 4 by 4 pixel area, for example, and it like averages the color across all 4 pixels, but it takes the brightness of the pixels and it sends the brightness in like a conventional way at the full resolution. So you have like a quarter of the color resolution, and then you have the full brightness resolution. So if you're trying to do like subpixel, I literally cannot show you subpixel stuff on the stream because the stream will delete all of it. So the only way to like show you subpixel stuff, if I were to like try to demonstrate it, would be to like get something subpixely working and then point a camera macro lens at the physical screen, zoomed in to the pixels. Which is, you know, difficult. But yeah, this was like floating around a few, like, I don't know. I remember seeing this like weeks and weeks and weeks and weeks ago. And if the date at the top of this thing is anything to go by, it's been around longer than that. We are kind of stuck in chibi mode. Yeah, if I squint at it hard enough. I think it works on my display. I'm not exactly about to claim that the blue is very readable, but I think my subpixel layout is compliant. Also, hello and welcome to Graffiti 82 and Encore. Ah! 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 Do you suppose that I could get it to display the subpixels? I'm gonna try and capture this with a camera. We're gonna grab the focus. We're gonna go all the way, let's see, I think it's macro, full macro, and then we're gonna zoom all the way in. And I'm like, you know, if you look at it through a camera, then you can actually read it. To be honest though, like, it's difficult. It's difficult for me to read in real life, especially the 4. But like, I mean, it works.